Conceptual Introduction to Matrices. Hello, everyone. Let us begin our session with a conceptual introduction to matrices. To start, consider that in our daily lives, we encounter vast amounts of information every single day. To make sense of this data and keep it organized, we often arrange it into tables. Now, in mathematics, when we want to handle this organized data more efficiently, particularly for the purpose of performing calculations and analysis, we use a specific structure called a matrix. Essentially, a matrix is a mathematical way of representing a table of numbers. The key advantage here is that it allows us to strip away the descriptive labels and focus purely on the numerical values. However, it does this while still preserving the relationship between those values based on their specific position within the structure. In the upcoming slides, we will walk through a step-by-step process to see exactly how we transform a standard data table into a formal matrix. From a table to a matrix, a step-by-step process. Now that we have established the conceptual definition of a matrix, let us move from the theory to a practical application. To understand exactly how a matrix is formed from raw data, we will examine a real-world example involving the inventory of stationery items owned by 3 different students. This will allow us to see the step-by-step transition from a standard data table to a formal mathematical matrix. Organizing data in a table. Now that we have established the general idea of organizing data, let us dive into the real-world example I mentioned in the previous slide. Imagine we are tracking the number of notebooks and pens owned by 3 students, Amit, Binu, and Chitra. To keep this information clear and organized, we can represent it in a standard table, as you see here on the screen. Looking at the data, we can see that Amit has 5 notebooks and 2 pens, Binu has 3 notebooks and 4 pens, and Chitra has 6 notebooks and 1 pen. Please take a moment to observe the structure of this table. In this layout, the rows, the horizontal lines, represent the individual students, while the columns, the vertical sections, represent the specific types of stationery they own. Understanding this arrangement is crucial, as we will soon see how this structure translates into a mathematical matrix. Removing descriptive labels. Now that we have our data neatly organized in a table, let's look at how we transition from a standard table to a mathematical structure. You will notice that in our table, we have labels such as student name, notebooks, and pens. While these headings are incredibly useful for us as humans to understand what the data represents, they are not necessary when we perform actual numerical computations or mathematical analysis. So, if we strip away these descriptive labels and focus only on the raw information, we are left with just the numerical data. Looking at the screen, you can see the numbers remaining in their original positions. In the first row, we have 5 and 2, in the second row, 3 and 4, and in the third row, 6 and 1. At this stage, we have the raw values, but they aren't yet a formal mathematical object. In the next step, we will see how to enclose these numbers to officially create what we call a matrix. Enclosing in square brackets. Now that we have stripped away the descriptive labels, as we saw in the previous step, we need to formally define this collection of numbers as a mathematical object. To do this, we simply enclose these values within square brackets. This resulting structure is what we call a matrix. Let us look at how the data from our stationery table is now represented. We denote this matrix as capital A, which equals a square bracket containing 3 rows of numbers. In the first row, we have 5 and 2, in the second row, we have 3 and 4, and in the third row, we have 6 and 1. By organizing the data this way, we have successfully transitioned from a descriptive table to a formal mathematical matrix. The importance of position. Now that we have successfully converted our table into a matrix, let us discuss a fundamental principle. One of the most critical aspects of a matrix is that the position of each number carries a specific meaning. You might be wondering, since we removed the descriptive labels like Amit or notebooks in the previous slides, how do we keep track of what the numbers actually represent? The answer is that the meaning is preserved by the exact location of the element within the structure. For example, look at the value 5. It is located in the first row and the first column. Because of this specific position, it still represents Amit's notebooks, just as it did in our original table. Similarly, the value 1 is located in the third row and the second column. This specific coordinate tells us that it still represents Chitra's pens. This leads us to the primary advantage of using this structure. Because the position of every element is fixed and consistent, we can perform complex mathematical operations on the entire set of data all at once, rather than having to treat each number as an individual piece of information. This efficiency is exactly why matrices are so powerful for data analysis. Key takeaways. First, let's look at the definition. A matrix is essentially a concise way of representing numerical data that is organized in a rectangular array. In terms of its structure, as we saw in our example with the student's stationery, a matrix is formed by removing the descriptive headers from a table and enclosing the remaining numerical values within square brackets. A very important point to remember is the positional meaning. Unlike a table where you have a label to tell you what a number represents, the meaning of a value in a matrix is derived solely from its specific location, specifically its row and column. Finally, regarding notation, you will notice that matrices are typically denoted by capital letters, such as capital A, capital B, or capital C. Now that we have walked through the process of converting a table into a matrix, let us summarize the key takeaways to ensure we have a solid foundation. With these core concepts in mind, let us move forward to the next slide, where we will discuss some common mistakes to avoid when working with matrices. Common mistakes to avoid. First, be careful not to confuse a standard table with a matrix. As we saw in our step-by-step process earlier, we started with a table containing names and item labels. However, a matrix is a purely mathematical object. This means you should never include descriptive labels, such as name or quantity, inside the matrix itself. Remember, a matrix contains only the elements, which are usually numbers or functions, and not the headings. Secondly, it is crucial that you do not ignore the order of the elements. Some beginners might be tempted to rearrange the numbers for convenience, but as we emphasized in the slide on the importance of position, the location of a number is what gives it meaning. For instance, in our example with Amit, Binu, and Chitra, if you were to swap the first and second columns, you would be swapping the counts of notebooks and pens, which would make your data completely incorrect. Finally, let's talk about the notation. While you might come across some older textbooks that use parentheses to enclose the data, the standard convention in the NCERT curriculum is to use square brackets. To ensure your work is formally correct, always use square brackets when denoting a matrix. Now that we have covered the basics and the key takeaways, let us conclude this introduction by discussing some common mistakes that students often make when first learning about matrices.